Section: Introduction. In this section, we discuss the advancements in large language models, LLMs, that have significantly improved reasoning abilities through a method called reinforcement learning with verifiable rewards, RLVR. Unlike traditional approaches that mimic reasoning steps, RLVR focuses on feedback based solely on outcomes, allowing for extensive learning across various tasks. A notable approach is the zero RLVR paradigm, which does not use any initial data from humans or AI for reasoning, applying RLVR directly to the base model with task rewards. However, these methods still rely on carefully curated question-answer pairs, which raises concerns about their long-term scalability as the demand for high-quality datasets grows. As AI systems evolve, relying solely on human-designed tasks may limit their ability to learn and grow independently. This highlights the need for a new approach that explores beyond human constraints. We propose the absolute zero paradigm, where the model learns to define and solve tasks that enhance its learning, enabling self-evolution through self-play without external data. Unlike previous self-play methods, Absolute Zero is designed for open-ended environments and uses environmental feedback as a reliable reward source, similar to how humans learn through interaction. Our proposed Absolute Zero Reasoner, AZR, creates and solves coding tasks in a grounded environment, ensuring task integrity and providing stable feedback. AZR constructs three types of coding tasks that correspond to different reasoning modes: induction, abduction, and deduction. We train the system end-to-end using a new reinforcement learning advantage estimator suited for multitasking. Remarkably, AZR performs well across various reasoning tasks in math and coding, even without in-domain data. In math, AZR competes well with models fine-tuned with specific supervision, and in coding, it sets a new performance benchmark, outperforming models trained with code datasets. We also observe several interesting findings. 1. Code priors enhance reasoning, as the coder variant of our model improved after training. 2. AZR shows stronger cross-domain transfer, significantly boosting math accuracy compared to expert code models. 3. Larger models yield greater performance gains, indicating that scaling is beneficial for AZR. 4. AZR generates intermediate plans as comments during coding tasks, suggesting that using scratchpads could be advantageous in other areas. 5. Different reasoning modes lead to distinct cognitive behaviors, with token counts increasing variably across tasks. 6. We note some concerning outputs from AZR, indicating a need for future work on safety-aware training. Section Summary. In this section, we introduce the Absolute Zero paradigm for reasoning models, which enables autonomous learning and self-evolution through self-play without relying on external data, thereby addressing scalability concerns in large language models. We present the Absolute Zero Reasoner, AZR, which constructs and solves coding tasks, demonstrating remarkable performance improvements in reasoning tasks without human-curated data, and highlighting the potential for general reasoning skills to emerge from self-interaction. Section: The Absolute Zero Paradigm. In this section, we introduce the Absolute Zero Paradigm. We begin with supervised fine-tuning, SFT, which requires datasets of task rationale answer demonstrations. Here, we have a query, a gold chain of thought, and a gold answer, all provided by human experts or advanced AI models. The model learns to mimic these responses to reduce the conditional negative log likelihood. However, at the highest level, we lack stronger models to learn from, and human labeling does not scale effectively. Next, we discuss reinforcement learning with verifiable rewards, RLVR. This approach only needs a dataset of tasks and answers, without labeled rationales. RLVR enables the model to create its own chain of thought and compute a verifiable reward based on the correct answer. Still, the dataset of queries and answers is labeled by human experts. The model's policy is optimized to maximize expected rewards. In summary, both SFT and RLVR depend on human-curated datasets, which limits scalability. The absolute zero paradigm addresses this by allowing the model to generate, solve, and learn from its own interactions through self-play. We propose the absolute zero paradigm, where the model simultaneously creates tasks, solves them, and learns from both processes without needing external data. It learns entirely through self-play, supported by an environment. We illustrate this paradigm, contrasting it with supervised learning and RLVR, showing how our method eliminates the need for human-curated data by enabling self-improvement through self-play. To clarify the absolute zero setting, we define how one model can act as both proposer and solver. We use a parameterized language model that plays these two roles during training. The proposer samples a task based on a variable, which is then validated to create a valid reasoning task with the environment. The solver then generates an answer. Each proposed task is scored by a learnability reward, reflecting the expected improvement after training on that task. The same policy also receives a solution reward for its answer, with the environment acting as the verifier. A coefficient balances the exploration of new tasks with improving reasoning and problem-solving skills. We shift the responsibility of scaling data from human experts to the proposer policy and the environment. These roles define and evolve the learning task distribution, validate tasks, and provide feedback for stable training. The variable helps generate tasks, and we can sample from a memory of past task answer pairs. We use a learnability reward to guide the proposing process, while the solver reward evaluates the correctness of the output. Together, these signals help the model propose challenging and learnable tasks, enhancing its reasoning abilities and enabling continuous improvement through self-play. We present the Absolute Zero Reasoner, AZR, as our first implementation of the Absolute Zero paradigm. In AZR, a unified language model serves as both proposer and solver, generating tasks to evolve its learning and attempting to solve them to enhance reasoning capabilities. The model learns to create tasks that challenge its reasoning while improving its solving skills. Within this self-play training, the model tackles three types of coding tasks, corresponding to abduction, deduction, and induction. We choose coding tasks due to the Turing completeness of programming languages and evidence that code-based training enhances reasoning. We use code as a flexible and verifiable medium for reliable task construction and verification. Finally, we update the model using a new advantage estimator designed for multitask learning. We outline the overall algorithm and provide an illustration of our approach. We also discuss several attempts that did not yield successful results but are still worth mentioning. Section Summary. In this section, we introduce the Absolute Zero paradigm, where a model autonomously proposes and solves tasks through self-play, eliminating the need for human-curated datasets. We present the Absolute Zero Reasoner, AZR, which functions as both proposer and solver, enhancing its reasoning capabilities by generating and tackling coding tasks that reflect fundamental reasoning modes. Section: Two Roles in One, Proposer and Solver. In this section, we discuss our approach of combining two roles, proposer and solver, within a single model. We find that large language models are well suited for this multitask learning framework, as they can formulate reasoning tasks and provide solutions in a shared language space. Our method involves rewarding the model for both creating tasks with high learning potential and effectively solving them, in line with the Absolute Zero objective. During each online rollout, the model proposes new reasoning tasks based on the type of task and a set of past examples it generated. We encourage the model to create diverse tasks that differ from previous examples, which helps cover a wider range of tasks. These proposals are then filtered and transformed into valid reasoning tasks that can be verified in the environment. After proposing tasks, the model attempts to solve them and receives feedback on its responses. Both proposing and solving tasks are trained using reinforcement learning. We design a reward system that emphasizes the importance of task difficulty for effective learning. Our reward for the proposer encourages the generation of tasks that are neither too easy nor impossible to solve. We use the same model in its solver role to assess how learnable a proposed task is, performing multiple simulations to calculate an average success rate. If a task is too easy or too hard, it provides little learning feedback. However, tasks of moderate difficulty, where the solver has some success, yield the most valuable learning signals. For the solver, we assign a straightforward binary reward based on whether its final output is correct. We then combine the rewards for both roles into a composite structure that includes penalties for format adherence. The tasks must follow a specific format, and only those that produce valid outputs are considered correctly formatted. We also explore different reasoning modes: deduction, induction, and abduction. We utilize a code executor as a flexible interface for constructing and validating reasoning tasks. We define a reasoning task as a triplet consisting of a program, an input, and the corresponding output produced by running the program with that input. In deduction, we predict the output based on a given program and input. The model generates a program input pair, and the environment computes the output. In abduction, we infer a plausible input given a program and an output, generating a new pair based on the task type. Lastly, in induction, we synthesize a program from a set of input-output examples, using a message to guide the solver in mapping hidden inputs to their outputs. Each reasoning task type leverages code as a clear and verifiable medium, aligning with our goal of creating self-improving systems in open-ended domains. We will now detail our algorithm. Section Summary. In this section, we describe how large language models can simultaneously propose and solve reasoning tasks within a unified framework, leveraging reinforcement learning to optimize both roles. We introduce a reward structure that encourages the generation of tasks with appropriate difficulty and detail the three reasoning modes: deduction, abduction, and induction, each focusing on different aspects of task triplets to enhance learning and problem-solving capabilities. Section: Absolute Zero Reasoner Learning Algorithm. In this section, we will explain our Absolute Zero Reasoner self-play algorithm, covering how we initialize and manage buffers, create valid tasks, validate solutions, and calculate advantage estimators. We will outline the self-play process of AZR. During the self-play phase, we utilize the task buffer in three main ways. First, we randomly select a set of past examples from the buffer to help the proposer generate a new task, encouraging diversity. Second, we take one example from both abduction and deduction buffers and present it to the induction proposer, which then creates a set of matching inputs and a natural language message. Lastly, to ensure stable training, if a batch of problems has fewer valid tasks than needed, we fill the gaps by sampling from previously validated tasks. The buffer expands whenever a valid triplet is proposed, regardless of whether a reward is given. For induction tasks, all valid triplets are also added to the buffer. Next, we describe how we validate tasks generated by our policy. For deduction and abduction tasks, each proposal includes a program and an input. We validate these by running the program with the input to obtain the correct output, forming a complete triplet. For induction tasks, we validate each input in the proposed set to create input-output pairs. A task is valid only if all inputs produce valid outputs and meet formatting requirements. The validation process includes checking program integrity by running the program to ensure it executes without errors, checking program safety by restricting the use of harmful packages, and ensuring determinism by confirming that the program produces the same output for the same input across multiple runs. We focus on deterministic programs to simplify verification, although we recognize the potential of stochastic programs for future versions. If a task proposal passes these checks, we consider it valid and present part of the triplet to the solver, using different formats depending on the task type. We use all valid tasks from the current time step, and if the batch is not full, we sample from previously validated tasks to complete it. Section Summary. In this section, we detail our Absolute Zero Reasoner (AZR) self-play algorithm, focusing on task proposal inputs, buffer management, and the validation of generated tasks. We describe how we construct valid tasks through a series of checks, ensuring that only deterministic programs are used, and outline the procedures for maintaining a stable training environment by managing task buffers effectively. Section: Answer Verification. In this section, we discuss how we verify answers for different tasks. For the abduction task, we receive a specific input from the solver policy and match it to a privileged gold standard using a probability function. We don't simply match the inputs directly because the probability function isn't always one-to-one. For the deduction task, we match outputs directly. In the induction task, we ensure that all outputs match a set of expected outputs. We acknowledge that this explanation might be complex, so we encourage readers to refer to our code examples for abduction, deduction, and induction verification. Next, we introduce Task Relative Reinforce++, or TRR++. In this approach, we train a combination of roles and task types within a multitask reinforcement learning framework. Instead of using a single global baseline, we compute separate baselines for each of the 6 task role combinations. This method blends individual question baselines with a global baseline, allowing for better variance reduction tailored to each task. The normalized advantage is calculated using the mean and standard deviation for each task type and role, resulting in 6 distinct baselines. For our training details, we initialize buffers as previously described and train our models with a batch size of 64 × 6. We use a constant learning rate and the ADAM-W optimizer, with a complete list of hyperparameters available in our documentation. Our main experiments involve training models on specific datasets, resulting in different versions of the absolute zero reasoner. In our evaluation protocol, we categorize datasets into in-distribution and out-of-distribution. We place more emphasis on out-of-distribution benchmarks, further dividing them into coding and mathematical reasoning tasks. For coding tasks, we use specific benchmarks, while for mathematical reasoning, we utilize several standard benchmarks. We ensure reproducibility by using greedy decoding for all methods. For our baselines, we use the Qwen 2.5-7b model and its specialized variants. We also include models trained specifically on code or math data. Our training data and initialization settings are summarized in our documentation. In follow-up experiments, we compare each AZR model to its corresponding base model due to the lack of established baselines. We then address our first research question regarding how AZR compares to other models trained with human expert data. Our results show that the Absolute Zero Reasoner Coder 7b achieves top performance in both overall and coding categories, surpassing previous models even without access to expert data. To evaluate cross-domain generalization, we compare math performance before and after training. Most expert code models showed minimal improvement, while our AZR models demonstrated significant gains, indicating strong general reasoning capabilities despite not being trained on human-defined tasks. Overall, our approach proves effective, showcasing the potential of our AZR models in reasoning tasks. Section Summary. In this section, we describe our approach to answer verification across abduction, deduction, and induction tasks, emphasizing the use of probabilistic matching rather than direct comparisons due to non-bijective mappings. We also introduce Task Relative Reinforce++, which computes separate baselines for different task role configurations, and detail our training and evaluation protocols, highlighting the superior performance of our absolute zero reasoner models compared to existing benchmarks, particularly in cross-domain generalization. Section: Research Question 2. How do initializing from different base model variants, base versus coder, affect performance? In this section, we explore how starting from different base model variants, specifically the coder versus the vanilla model, impacts performance. Our findings indicate that the coder variant performed better overall in both math and coding after the AZR self-play process. Interestingly, even though the coder model initially had a lower average performance in math compared to the vanilla model, it surpassed it after AZR training. This suggests that having a solid foundation in coding can significantly boost broader reasoning skills within the Absolute Zero Reasoner framework. Next, we investigate how changing the model size affects AZR's performance in both in-distribution and out-of-distribution scenarios. We analyze various model sizes, including smaller and larger variants, and find that larger models tend to show more significant performance improvements. For instance, the 7B and 14B models continued to improve with more training steps, while the smaller 3B model reached a plateau. In out-of-distribution tasks, larger models also outperformed smaller ones, indicating that scaling up enhances AZR's effectiveness. We plan to further explore the scaling laws that influence performance in the absolute zero paradigm. We also assess our method using a different model class, specifically Llama 3.1 to 8B. Although this model is less capable than the Qwen 2.5 models, we still observe moderate improvements, demonstrating that AZR can be effective even with weaker models. However, the gains are not as pronounced, which aligns with our earlier findings that performance improvements are linked to the initial strength of the base model. During AZR training, we notice intriguing response patterns in both the proposal and solution stages. The model generates a variety of programs, tackling tasks like string manipulation and dynamic programming. For example, it successfully proposes a code problem that finds the sum of continuous subarrays matching a target value and solves it through trial and error. We observe distinct reasoning patterns based on the task type, such as self-correcting during abduction tasks and systematically checking test cases when inducing programs. Additionally, we find that the final code outputs often include comments that resemble step-by-step plans, similar to the React prompting framework. This behavior suggests that intermediate planning may enhance final answers, and we believe it could be beneficial to encourage this in long-form responses across various domains. We also notice emergent cognitive patterns in the Llama 3.1-8B model, including clear state tracking behavior. However, we encounter some concerning outputs, which we refer to as uh-oh moments, prompting us to recommend further investigation into their implications. Lastly, we observe that token length increases during training, with variations depending on the type of cognitive task. The most significant growth occurs in abduction tasks, indicating that the differences in token length are reflective of task-specific reasoning behaviors rather than random occurrences. Section Summary. In this section, we explore how different base model variants and sizes impact performance, finding that the coder variant outperforms the vanilla model after training, and larger models show greater performance gains in both in-distribution and out-of-distribution settings. We also observe interesting cognitive behaviors during training, such as intermediate planning in code responses and task-specific variations in token length growth, highlighting the nuanced reasoning patterns of the models. Section. Research Question 7. How much do the designs of Proposer contribute to the overall performance, ablation? In this section, we explore our 7th research question. How much do the designs of the Proposer contribute to overall performance? To investigate this, we analyze two components of the Proposer role and present our findings in a table. First, we assess the necessity of conditioning on historical reference triplets. We create a version that uses a fixed prompt for proposing tasks instead of dynamically conditioning on a set of historical triplets. This change leads to a significant drop in math performance and a slight decrease in code performance, indicating that dynamically using reference programs likely enhances performance by increasing diversity and coverage of reasoning problems. Next, we examine a scenario where we do not train the Proposer at all, relying solely on the current learner and training the solver independently. This results in a moderate decline in overall performance, suggesting that while training the Proposer is helpful, it may not be the most crucial aspect in our framework. We think this could be linked to task interference, as discussed in multitask learning literature, and we see potential for further research to strengthen the Proposer. Additionally, we present extra results, including detailed scores from out-of-distribution benchmarks during training for both the 7B and 14B models. We also report in-distribution benchmark performance for the 7B model. We encourage readers to check out other sections where we discuss various experimental directions that, although not yielding significant performance improvements, provided valuable insights. We also discussed the use of reinforcement learning, RL, to enhance reasoning capabilities in large language models. One notable approach is STAR, which uses expert iteration and rejection sampling to improve the model's reasoning iteratively. A significant work, referred to as O1, was among the first to apply this method on a large scale, achieving top results in reasoning tasks. More recently, the R1 model has matched or exceeded O1's performance, introducing a zero setting where RL is applied directly to the base model. This has inspired further research, including attempts to replicate or enhance the RL algorithms. We extend the zero setting to a new absolute zero setting, where the RL process starts from a base model without any fine-tuning or external prompts. All data for improving reasoning comes from self-generated proposals, refined entirely through RL. Our aim is not just to match zero-setting models but to surpass them over time. We also delve into the self-play paradigm, which dates back to the early 2000s, where a proposal agent creates questions for a prediction agent to answer, leading to continuous improvement for both. AlphaGo and AlphaZero applied this concept to the game of Go, showcasing superhuman performance. Various methods, including asymmetric self-play and unsupervised reinforcement learning, focus on creating new tasks for agents to learn from without supervision. Generative adversarial networks also fit into this paradigm, where a discriminator distinguishes between real and generated data. Recent works like SPIN and self-rewarding language models utilize the same language models as reward models to enhance their generative and discriminative abilities. Our work builds on the self-play paradigm, being the first to use it for eliciting longer chains of thought to improve reasoning, framing the problem as tasks involving Python input, output, and function abduction, deduction, and induction, all within an operational environment to support RL. Section Summary. In this section, we investigate the impact of proposer design on overall performance through ablation studies, revealing that dynamically conditioning on historical triplets enhances performance, while training the proposer is beneficial but not critical. We also explore additional results and advancements in reasoning capabilities using reinforcement learning and self-play, highlighting our novel approach to improve reasoning through long chains of thought in a structured environment. Section: Weak to Strong Supervision. In this section, we explore the idea of weak to strong supervision, which has been examined in previous research. In those studies, a teacher, even if less capable than the learner, still provides valuable guidance. We look at a similar scenario where the learner might have superhuman abilities. Instead of depending on a weaker teacher for supervision, we suggest a different method, using verifiable rewards to guide the learner's progress. This approach could offer a more dependable and scalable way to learn. Additionally, in our method, the learner generates its own learning tasks and goals without any external guidance, allowing it to enhance its learning through self-directed practice.